So this talk is going to be about learning policies from self-play with policy gradients and MCTS value estimates, as you can see in the title. It's joint work with Eric, Piette, Matthew, and Cameron, who are sitting over there. It's a part of the Digital Looting project, which I'm not going to expand on too much in this talk, because it can also be viewed as a standalone presentation. There's going to be a lot more on the Digital Looting project in a separate session tomorrow, so I would recommend going to that one. But for now, this paper. So we're going to be doing learning from self-play and in games. And we've seen some successes doing that throughout history, with some famous papers like TD Gammon, more recently AlphaGo, the follow-ups of AlphaGo, AlphaGo Zero, AlphaZero, etc. And in these self-play training algorithms, we use an objective function which we're optimizing. And I started wondering, like, what objective function should we use? Like in recent years, we've mostly been trending towards the cross-entropy objective, which was very successful in AlphaGo, AlphaGo Zero actually, and AlphaZero. And well, everyone pretty much keeps using that because it works very well. But I think we should first ask, like, why are we learning our policy before we can actually answer which objective function should we be optimizing? And there are multiple different reasons why you might want to learn your policy. You might want to learn a standalone policy and just have it play without anything else. You might want to plug it into a search algorithm like MCTS, as we've seen in AlphaZero. And then you might want this combination of the search with the policy to maximize its playing strength, which is different from maximizing just the standalone policy's playing strength. A different use case that we're also interested in this project is that we want to learn a policy and then we want to interpret like the strategy that has been learned inside this policy. And I think we might need different objectives for all of these cases. So I've got something that looks a little bit scary here, but it should be fine. And really the most important part is the intuition that I put at the top here. So the intuition of like this standard RL objective, which we always like optimize in the standard reinforcement learning setting, it's just to maximize the expected rewards that you gather over your episodes. So it's an expectation over an infinite sum. In games, we usually set the discount factor to 0. In games, we usually only have a single point in time where you get a non-zero reward, which would like be a terminal game state. The S0 is S0. That's just formally acknowledging that in a Markov decision process that we depend on like what's the initial game state. And with 80 like sampled from pi, I mean that all of the actions at every time step t is assumed to be sampled from a policy pi, and pi is the policy that we're also optimizing. So TD Gammon and AlphaGo, for example, they maximize this objective. In TD Gammon, it's like indirect because they're like optimizing a value function, and then you maximize over your values, and then you're indirectly doing this. With AlphaGo, it's you directly take this objective function and you try to differentiate it with reinforce, and then you directly optimize this. So a different objective function that we've been seeing is what I just mentioned, the cross-entropy objective function, which is being optimized in AlphaZero and AlphaGo Zero. And I've changed the notation a little bit. But basically with the fancy M, I mean like the behavior of MCTS, and I view it as a policy. And pi is again the policy that we're optimizing. So M is the vector of visit counts divided by the visit counts of the parent node, of the root node, and then you transform this into a distribution, basically. And with cross-entropy, you basically just try to match these two different probability distributions, so you try to match the policy that you're training, and you try to match it with the MCTS distribution, so you're basically mimicking MCTS. And at the end, you see the gray box, I say that we sample all of the actions AT from Monte-Carlo tree search, which is what we're doing in this AlphaZero style self-play training, We play games using MCTS with the policy inside it already. So yeah, that's what these algorithms try to optimize. And if I compare these two objective functions to each other, then an advantage for me of the standard RL objective is that it's very intuitively appealing. You're just trying to maximize your rewards. Well, it can't get much simpler than that. But the disadvantage is that you often need like little tricks to stabilize the self-play training, because you can get like into cyclic strategies which beat each other, like in rock, paper, scissors. So you need to use tricks like randomizing over multiple different opponents in your self-play, for example. And then if I look similarly at the cross-entropy objective, well, a big advantage is that it gets state-of-the-art results, so it performs really well. And it's nice that this advice that you get from MCTS by trying to mimic it, that this is hypothesized to stabilize the self-play training. So you don't need any extra tricks, you don't need to randomize over a distribution over a self-play like practice partners. You can just play against yourself. But one thing I didn't like about this cross-entropy objective is that, well, we're mimicking MCTS, but MCTS by design, it's also doing exploration. It's not just trying to maximize the rewards. And if we're trying to mimic this MCTS behavior with our policy, this means that our trained policy is also learning to explore. And I don't know if we always want that. So if we want to maximize the playing strength of a standalone policy, do we want it to be exploring? Probably not. If we want to plug it inside different parts of MCTS, then the answer becomes a bit different. If we plug it inside the selection phase of MCTS, well, that's where MCTS needs to do its balance between exploration and exploitation. So it's good if our policy also does this. If we plug it into the playout, I wasn't really sure. Like, intuitively, it makes sense that you want your playouts to just maximize playing strength, and then you maybe wouldn't want it to explore. But we've seen some older work on what's called Monte-Carlo simulation balancing, in which it turned out that just strictly optimizing for trying to have an optimal player as a playout policy, that's not always best. So sometimes you may want it to explore a little bit. That's at least turned out to work well in practice. So now we are moving on to a different objective function which we propose in this paper, the research policy gradient objective. And the intuition behind this objective is that we want to maximize the expected rewards that we gather over our episodes, but we want to maximize the ones as predicted by MCTS, so not the rewards that we actually obtain, but just what MCTS predicts for us. And the nice thing about this is that it turns out that we still get this advice from MCTS, which I think helps to stabilize your self-play training process. But we're no longer mimicking MCTS, so we may no longer get this exploratory behavior. So what it looks like mathematically is that you take this expectation. I've moved it inside sum because that's more convenient mathematically. And inside this expectation, we always have like one action that's picked by the policy at a time step t. All of the actions before t are assumed to be picked by MCTS, and all of the ones after t are also assumed to be picked by MCTS. And this means that we can use the state distribution that we encounter in MCTS self-play for training, and it also means that we can use the MCTS value estimates. So we can derive this using something very similar to the policy gradient theorem by Sutton in 2000. I'm not putting the math in here. I've got one slide back up for that if anyone wants to see what does this gradient of this objective function look like. So if you want to see that, you can ask me afterwards or check it in the paper. But yeah, we can differentiate this objective function, which means that we can optimize it using gradient descent. And we can estimate this function that we get, and the estimator ends up looking very similar to the mean actor critic, if anyone's familiar with that. So it's kind of like an actor critic, but we will have MCTS as our critic instead of like a queue function as we usually see. So we've done some experiments with this. I'm putting 6 plots on there now. We've done actually experiments in 10 different games, but then the plots become kind of unreadable, so I'm using just 6 games in the slides, and you can see the other 4 games in the paper. So what we see in these first plots is the orange curve. That's the win percentage in all of these different games over training time on the x-axis. And it's the win percentage of the new objective that we propose versus a policy trained with the cross-entropy objective. The blue one is another slightly different baseline, which was necessary because of another detailed trick, which you can see in the paper. But basically, you see that all of the orange curves quickly go above 50% above the blue one, which means that as a standalone policy, we get a much stronger one with our new objective than with the cross-entropy one, which makes sense because we're no longer doing this exploration that the cross-entropy objective does lead to. So we've also tried to use these trained policies inside MCTS. I've tried it very briefly to put them inside the selection phase. I didn't expect it to work. It doesn't work. You need exploration in your selection phase. So if you put a policy in there which doesn't explore, then that's terrible. Don't do that at home. But I've tried also plugging it in as a playout policy, which seemed more reasonable to me. A playout policy, I think that's fine if it doesn't explore. And it got slightly worse performance than the cross-entropy policy. Very slightly. So it's almost the same. In most games, it's not statistically significant. In a couple of games, it was like just barely statistically significant. But it seems that the cross-entropy objective may still be better as a playout policy, which again might be related to the simulation balancing thing that I've mentioned before, which you can see some references at the bottom. So next we're going to look at the entropy of these policies as they are playing. So the entropy basically means high entropy in your policy means that you're kind of playing randomly. Low entropy means that you're almost like deterministic, that your policy really knows what does it want to play. And in all of these games, we basically see at the top, we see a standard UCT agent, upper confidence bounds applied to trees, just the standard MCTS agent. And it's almost playing randomly, so in many of these games, it's not very strong. It's got very high entropy throughout the game. A little bit below that, the blue curve, that's actually the cross-entropy one, which is trying to mimic the MCTS behavior. It's often still got very high entropy, so often it's behaving like not randomly, it's below the top, but it's playing somewhat closer to random. And below that, we get our biased MCTS agent, which uses in an AlphaZero-like style, it uses these trained policies. And below that, we get our new objective function. So it really always has the lowest entropy, which means that it's not doing much exploration. It's always quite sure about a few moves that it may want to pick, and it doesn't care about any other moves. So it really doesn't have this exploratory behavior anymore. And finally, we're going to look at like the density of the features. We use a feature vector, where we're not doing neural networks, just a linear feature vector. And we're looking at the density of values, like the weights that are assigned to these features. The blue one, that's cross-entropy. You see a very high peak around 0, which means that almost all of the features get a weight close to 0, that they're all the same weights. And the orange one, you see, it's much wider, much less of a peak around 0, which means that it's using more of the features. It's more capable of distinguishing between these different features. And we hope, that this will help to explain a strategy, to extract a strategy from these learned policies. Because the features have more different weights. The features don't all look the same. There's really a clear few favorite features. So we hope that we can extract strategies from them and interpret them. So to conclude, learning to explore, it's bad for standalone playing strength, that's fairly obvious. Crucial for selection policy, turns out to be helpful for playout. But we have reasons to believe that removing this exploration may help to interpret strategies better. Thank you.
Thank you very much. Perfect timing, exactly 15 minutes. Okay, questions. We have 5 minutes time for questions.
Just a very simple question. So in one of your slides you say at time t you use the learned policy, and at all other times you use the MCTS policy. Does that mean you're using it just for selection, in other words?
It's in the objective function, so it's not how we're actually playing in self-play, okay, but it's just inside the objective function. And it looks a little bit magical here, I guess. But when you derive it, when you differentiate this, you end up with a gradient expression, which, in my opinion, looks really nice.
Sounds like maybe one of those people that needs to see the maths, yeah.
That's what the gradient expression ends up looking like. So it's like the state distribution that you encounter in MCTS self-play, which is exactly what you also get with like the reinforced policy gradient theorem. And at the end, we get the value estimates as predicted by MCTS for the children of the root node.
Thank you.
So, another question. Rob, can you be loud?
Yes. How about sparse, rewarding environments? Hi. How about your system when it runs in sparse, rewarding environments?
So we've actually only run it in sparse reward settings because we've only been running it in these board games where you just get a reward of 1 at the end if you win, and you get a reward of -1 if you lose. And in all other time steps, we actually don't get any rewards. So that's the experiments we ran. Just for the theoretical parts, I like to stick true to the reinforcement learning like terminology. So that's why we've got all the intermediate rewards. But in our experiments, we didn't use that. So we've only used sparse rewards.
Good, thanks. More questions? Oh, there's one up there. And faster. After all the food.
Hello. Couldn't you use another version of MCTS that does something closer to off-policy search? Or rebalances the search in some kind of... I mean, something that doesn't explode that much? Or doesn't backpropagate exploratory rewards?
You mean to provide the value estimates?
Yes.
Or?
Yeah. So provide value estimates that come from something akin to an MCTS version of Q-learning. Mm-hmm. Yeah, that wouldn't explore.
So it doesn't have to be MCTS. I just used the symbol M for MCTS, but you could plug in any other thing that generates value estimates that you like. I still believe that the search on top of the policies, as we've seen in AlphaZero, I think it's really important to stabilize your self-play training, the search. So I think that if there's no search at all, that it might not lead to stable training, but we didn't try that.
Okay, so time is over. Thank you very much again. So the next talk will be presented by Vanessa. Slowly. We have time. So for those who came later, we will collect the last page of the program. Contains a list of papers. You will mark only one of them, and we will collect them, as Dan is showing, and here. We will collect them after the second session here, and please mark only one of them. Thanks. So Vanessa, great. You can start.
Oh, sorry. I did already start. Okay. Hi. So I will be talking to you today about simulating human decisions in game analysis. So basically applications where you simulate human decisions. So if you use an AI instead of running large user studies, for example, and you're using the observation you make on the AI to, in the context with human actors, actually. So think basically a car crash dummy. You want to not ideally use humans for these tests, but you will actually put humans in the cars later. But in this case, it's about decisions and not just existing or something. So these things are actually everywhere, from the car crash testing to public transit systems, but they're also in games, and which I'll get to in a second. The thing is, many times the potential errors, and I think we can agree that our potential errors are not considered specifically or systematically, and so this is why there's the vision thing in here. This is actually kind of more a vision paper. So I'm just trying to make the case of we should be looking into this more and how can we possibly approach this. So let me start off with a couple of examples of simulated human decisions in the games area. And it's actually pretty common. So we had self-play in the keynote and also just in the previous talk, where your AI is using itself for training purposes, but then you want to actually play. So you're trying to improve your performance by playing against yourself, but you're actually trying to improve your performance against human players. And a similar topic is opponent models in statistical forward planning, where you're trying to predict your opponent's movements, but they usually are an AI in training, but might be a human in practice. We also got PCG, where lots of the evaluation of the generated content, or games, or levels, or whatever you have, are based on simulations. So if you want to try to figure out how difficult something is, or whether it's playable, that might be based on an AI. And a thing that's a bit further away from this is emergent narrative. So if I'm playing The Sims, the other Sims are usually also simulated human decisions, so it looks like I'm within this world. So I'm not trying to bash this. We've been using this, and possibly in many cases it's just the only solution that's feasible, and it has been very successful, as DeepMind has demonstrated. I'm just trying to look at it. So first thing I found is there's two common approaches of how this simulated data is used. The first one is directly using the data you get to inform whatever you're trying to do. So for example, if I want to assess the difficulty of a StarCraft 2 campaign, I might just have AIs run through it and compare these win rates, and whatever the win rates are lower, I think maybe the campaign is a bit harder, so I can try to get a difficulty curve, for example. So some of these cases, especially if I want to do it online, this might still be too expensive. So in these cases, model-based approaches are usually seen. So instead of using this data that you generate with simulations directly, you just train a supervised learning model on it and can use that within runtime. So that's all great. Thing is, what you can see here is me and the Baumgarten AI playing Mario on Ahmed's new framework. And I'm not sure whether you can guess who's me. It's not obvious at all. Yeah, so you see my point, right? And another example would be I'm still going, okay. Anyway, the DeepMind bot, there was a large discussion about the APM, so the actions per minute. They were actually restricted, but the way they are distributed is still very different from what human players, like even pro players, play. So if I completely rely on the similarity of my AI simulations or the simulated human decisions, but they actually misalign with human behavior, I might run into a problem if I trust it. So that's kind of obvious, and I'm not saying that this might hurt the case too much. The AI simulations just have to be similar enough in certain aspects that I need them to be. But in all cases, what we're really doing is assuming that whatever we are measuring from the simulated decisions is generalizable to whatever I'm using them within the human context. So let's look at this with an example. In the StarCraft self-play training, right? The assumption is that if I will improve my gameplay against an AI, then I will also be better against a human. And I guess this worked out rather neatly. But we've been actually looking at related work that has been approaching these potential misalignments. And what we mainly found is that research tries to focus on reducing the error, or like reducing this alignment. So for the direct approaches, so remember if you use the data directly, here are two examples of what has been done. So there's restricted play, which is a framework of posing questions, basically. So you can ask, well, is this specific thing that I've added to my level, is it hurting fairness? So you can have an AI that uses it and one that doesn't use it. So it's like a very structured way of posing the questions and trying to reduce the error that way. And in the StarCraft self-play from DeepMind, we have diversification, and I think David Silva did touch on that too. So you basically introduce additional objectives and maybe some noise. So stuff like you would do in Convolution a lot. So that's for the direct one. For the model-based one, if you can actually get hold of data from humans, you can mix this data into your training, or you can at least validate your model. And that has been done quite a fair bit as well. The third category, which basically fits both of these approaches, is human-like AI, and there's also lots of new research going into this direction, figuring out how to model types or personas and creating human-like AI in the sense that it behaves like humans. So we didn't want to do this. We wanted to take a different approach, which is just learning more about this error instead of reducing it. Because I think at this moment in time, we probably can't reduce it to zero. So why don't we try to understand it properly and figure out whether we can handle it within our approaches. So for this, we looked at an example, and we stuck with StarCraft 2. Mainly because for this example, we needed lots of data for both AI players and human players. And with the release of the SC2 API, there's lots of data available now and ways to process them. So that's exactly what we did. We collected 3 data sets, one from the ladder, so that's the normal people playing. We got the World Championship Series, so that's the pro players, and an AI ladder. We certainly didn't get the DeepMind plays, but it's something. And we processed them through the SC2 API, and then you can basically, per game tick, get a representation of the game state, which usually represents something like the resource production, units in terms of resources, like very high-level stuff, like how much gold you have, whatever, stuff like that. And the first thing we did is we looked into the distribution of these features, and we expressed them with histograms, and you can see this is a histogram, like an example of it. We compared them pairwise between the different data sets. So here in this case, you can see the red one is from an AI, and the blue one is from the ladder, and the purple ones are where they overlap. So they seem, visually, they seem very different. We also did confirm this with statistical tests. So they're statistically significantly different. There are a few outliers, but for most features that's true. But the question is, I mean, that doesn't necessarily mean that the generalization doesn't work at all, but we wanted to investigate it more with a couple of use cases. So the first one is, if you imagine you create a new map, and you want to figure out whether it's balanced for the different races in StarCraft. Ideally, you want to do this before the release, so you might want to use a couple of AI simulations to figure out what win rates the different races have in order to identify potential balancing issues. So this would be a direct approach, and we did this with 5 maps from the ladder data set. And as you can see, for all of those anonymous 5 maps, we get, for all of the races on the top here, we get about 50% win rates. Looks perfectly fine. We did the same thing on the AI data set. Very different picture. There's not actually one map that would be balanced, like around 50% for the AI data set. So from that, we would have to, if we just looked at that data set, we would have had to conclude that the generalization is not possible because the result is really different. We also wanted to look at a model-based approach. So a use case for this is actually based on previous work with Mike. It's about win predictions within an agent, so embodied win prediction, where you... this is actually used in DeepMind's bot too, so they have some component that tries to figure out how good the game state is based on how likely they think they're going to win. And so this is very useful. But what we actually want to do is we want to train this win prediction on an AI, but then we play against a human player, and we still want this win prediction to hold. So this is the task. We first produced some baseline results where we just trained prediction algorithms or machine learning algorithm on the 3 different data sets separately. And because this is at the end of the games, we get very good predictions. This is not actually the interesting part. The part where we then cross over the results. So we train on one type of data set and then use it on the other. You can see the win prediction accuracy is like random, basically. So it drops off a lot from the 90% we got over there. So this would mean generalization is again not possible. I actually have an interesting tidbit because if you compare, do a crossover between the 2 human data sets, even though some of them are pro players and probably behave a bit differently than the normal, you still get pretty good prediction accuracies, but not with the AIs. So from this, we would have to conclude that from this example study, at least in this case, we see significantly different behavior between AIs and humans. They have clear effects on the use cases that we looked at, and the generalization is not possible. In order to not be a hypocrite, though, we should probably think about whether these use cases generalize. And so, for example, Alpha Star might have more human-like behavior than this AI on the ladder. So that's a thing we can't answer right now. But what we can say is that counterexamples exist to where these approaches don't work. And so I think that's a strong case for saying that these sanity checks of figuring out, doing experiments like these where the data sets are compared is worthwhile. I want to conclude with the vision I have from this in the longer term and the short term. I think, as I said, data-driven analysis is worthwhile. It could help understand a lot of approaches. It might be possible to use optimization under uncertainty, such as surrogate-assisted algorithms, for example, Sapeo, and there will be a video on how that could be realized. And for the longer term, it might be good, I've been harping on about this, but like to have a concerted effort and gather all the data in one place and hopefully work on this together.
Thank you very much. So questions? 5 minutes for questions. Dan.
So, should people see you if they want to join this task force?
Oh yeah, I put it on. Yes, they should. Or Dan. Yeah.
Or Vanessa.
Yeah. So the task force is a way of organizing, gathering this data, and like putting up a website, and
maybe having a special session on these issues.
Or like a Dutch Door or a Lawrence Center. Yep.
Julia.
Should I speak?
Try.
So, okay, so I didn't quite get it. What is the main difference between Christopher Holmgaard's procedural personas framework in testing both AI agents playstyle against each other and against humans on different agreement ratio?
This is part of it. I mean, I did actually put the AI personas in there somewhere. Right. As far as I understood it, it's about reducing the error more, and
it's about characterizing
with human data.
Yeah.
Okay, I thought it was basically figuring out based on theories and then implementing the personas, and then so not actually comparing to observed human data.
There's one way of doing it is like taking play traces
Mm-hmm.
and then looking at the agreement ratio in different ways and seeing to find a way of making the personas play like the humans on this chosen agreement ratio.
So how is that measured? Because as far as I know, the only thing that is measurable is the actual difference between like one single action, and that doesn't actually represent how the human behavior, right?
There's action agreement ratio, tactical, strategy agreement. But we can take it offline. I mean, we can get to dig down a bit further.
Okay. More questions? Okay, so if there's no more question, thank you again, Vanessa. So you can use the mic, yes. But here there's this is a microphone. Okay. So when you are loud enough.
Voice is really loud.
It's
Yeah.
fine. Okay, then you can start.
Hi, my name is Kyungjin Park, and I'm a PhD student in North Carolina State University. I'm going to present my work today. So, an educational game is a promising tool for education and training. Immersive games and educational games are being used to help engage students in situated problem solving, and they support adaptive instruction, and they promote engaged learning in both in classroom setting and the informal setting. So the common design approach for the educational game is to provide a series of challenges that are progressively advanced. However, students come to educational games with the different levels of knowledge. So there are students who, I guess my voice is. So there are students who are unable to master the prior learning objectives. They might either give up playing or take trial and error approach to achieve the goal. Also, student diverge in the gaming experience. So some students might look for exciting gaming experience because they love the games. But others, students who do not like games or they don't have much experience in the game, they might have challenges if they present with difficulty gameplay challenges. Thus, there's a definite need for the personalized learning experience to support mastery learning and engagement. So in order to do that, we have to generate lots of levels, but this requires a large amount of time and effort for the human developers. So we look for the way of generating levels automatically utilizing the procedural content generation approach that has been received lots of attention in the game industry and the research area. So we expect the automatic level generation in educational games can provide adaptive environment, a master learning environment, and created levels, and also the replayability of the game. And this is the overall framework of how we want to apply the level generation in the educational game. And throughout the students' gameplay, the student model is maintained to look at all the students' actions in the game. And it extracts all individual students' learning competencies and the gaming skill that will be the basis of the level generator. And then it generates the unique game level until students master the specific concepts in the game environment. So in this work, this is the very initial phase of the whole research. So we're focusing on building a good performing level generator. So the generator will be based on GAN, which I'll explain more in detail. So this is the outline of my work. So there have been lots of various PCG approaches taken in the area of entertainment games, from search-based to machine learning methods. Meanwhile, researchers have started exploring the application of PCG to educational games. However, there are not much work that has investigated creating levels from machine learning approach. So in this work, we are utilizing the convolutional GANs that was based upon Volz and colleagues' work, who just presented. And the method we're taking is not taking their evolutionary strategy, but we are focusing on enhancing the performance of the generator. Next, I'll introduce Engage, our game-based learning environment. So Engage is a game-based learning environment that was designed to promote middle school computer science education. And it takes roughly 10 hours of gameplay where the students are presented with the computational challenges and platforming elements throughout the game. And Engage has been used in a number of classroom studies where we found that it produces statistically significant learning gains from the pre- and post tests. So this is the backstory of the Engage. So when the game starts, students learn that an underwater research station has been taken over by a rogue scientist. So they play the role of the protagonist who is sent to this research station to investigate the situation and reestablish the facilities. So throughout the game, students interact with the non-player characters who provide scaffolding, and they progress through a series of rooms, each featuring a set of computational challenges, and they have to solve with this visual block-based programming. Then why is that Engage is such an interesting test bed for the PCG? Like I mentioned, Engage has been used in a large number of classroom studies where students show a wide range of experience, performance, and abilities in the game. So we thought being able to generate levels that are targeting this wide range of students' ability is critical for providing effective learning experience. So this is a short video of a room in Engage. So we focused on generating levels in this type of room and authored levels that contain the gaming skills and computational concepts that are required in Engage. This specific room requires students to pair with the platform device to program it to move across the water field obstacle. Students can solve this challenge by creating a program that instructs the platform to move forward 4 times and wait 1 minute. Here you can see the platform moves following the student's program, and their character gets to escape this room. So for having the data for training the model, we took the level representation that was used for 2D tile-based representation, has been used for lots of platformer games such as Super Mario Bros. Or Angry Birds. So this 3D environment can be viewed as 2D from the top-down view. And we defined the symbols for each of the tile type in the game, and that was converted to a text format and the color map. And this specific room does not require students to program loops or conditional that are required in Engage. So we added 2 other barriers so we can have variations to provide the students the level that encourage the students get those concepts. Next, I'll dive into our GAN-based level generator. And deep convolutional GAN we are using in this work is a variant of GAN which performs a type of zero-sum game where a generator and a discriminator are trained to outperform the other. So DC GAN uses transposed convolutional layers for the generator and the normal convolutional layer for the discriminator. The purpose of training a GAN in general is to enhance the performance of the generator so that it could generate more real-looking synthetic data that is able to forge the discriminator. I guess most of you are familiar with GAN, but some of you who might not, I'll explain how it trains in terms of our level generation work. So for each of the training phase, the generator takes a random noise vector and generates the synthetic levels that could fool the discriminator. And the discriminator takes input from either the original level and the synthetic level and discriminates which one is real or fake. And in our multi-step approach, we train this model like twice, where the first step DC GAN is for augmenting the data set, and the second step DC GAN is for supporting the higher solvable level generation. Let's see how it works. So we first train with the original levels, and the trained generator generates lots of levels. And then, so some of them might not be solvable, so we take this set and it goes through the solver. And we just take only solvable levels, and that is added to the original levels as a process of data set augmentation. Then with this augmented data set, we train another generator and then get another levels. So the reason we are doing this is that the convolutional layer that was used for this GAN, there's like lots of parameters to train, so we thought, but it requires a large amounts of data to like have this kind of model to be effective. So the advantage of the multi-step DC GAN is that generating the levels that we could, so that we could train other model to be effective at producing the better generated levels. Now let's see how we evaluate our model. So we took the 2 approaches from the single step and the multi-step with different kinds of data sets. So see if the data set augmentation enhances the performance of the model. The evaluation metrics we used is solvability and the novelty, and I'll explain each of the details. So for checking the solvability, we developed the solver module that checks the generated level is solvable by checking the 5 constraints. So first, these 4 points should be unique within a level. Second, there should be a path from the starting point to the pairing point, and the pairing point to the moving platform. And for the moving platform, there should be the way to the other side of the level, and there is a way from this point to the exit point of the level. Secondly, we measure the novelty of the generated levels that was adopted from Lehman and Stanley's novelty search work. And this novelty row for the level X is given by this equation, where mu I is the ith nearest neighbor drawn from the original data set with respect to the distance heuristic. And this distance heuristic was adopted from Wiebe and colleagues' work, where the distance between the two tile-based level is defined as the number of mismatched tiles at the same coordinate divided by the total number of tiles in the level. And these are some of the examples that generated solvable levels and generated unsolvable levels. And the result shows that there's a statistically significant enhancement in solvability. It's achieved by the multi-step again with 250 epochs of training. However, there's a minor reduction in the novelty score. But this reduction means that only 2 or 3 tiles different. So by sacrificing the 2 or 3 tiles different, we were getting significantly higher solvable level. So I think it's good. So, and there are 3 takeaways from this talk. Utilizing the procedural content generation in educational games has considerable potential for increasing adaptivity and replayability. And the convolutional GANs are a promising vehicle for the PCG in educational games. Multi-step GANs significantly enhance the solvability of the generative levels with a minor reduction in novelty. So in the future, we'll investigate other models such as conditional GAN and self-attention GAN and also other machine learning approaches. And we'll incorporate ability to generate levels that addresses specific learning objectives. And in final, we'll incorporate student model to enable adaptive runtime level generation. And yeah, that's thanks to my colleague, and that's it.
So thank you. Questions? So there is up there one. Where was it? It's very good.
Thank you for your work. Interesting presentation. I wanted to ask you, though, you mentioned solvability as basically a pathfinding, whether you can get from A to B, etc. But the main educational, the task is to find some sort of programming path that, is that actually feasible? And is it feasible for what kind of level of, you know, how deep in the computational model, in the interface you have to go?
So just the solvability, it checks if it's like a playability in the platformer games. So it just checks basically if there's a way. But if we want to check any computational concept, so that's actually the direction I'm going right now. So it's actually we have to like figure out what kind of like pattern we should care to like check those loops or conditional concepts. If that answers the question.
So, thank you for a very interesting presentation. I was just wondering whether the GAN was really necessary for what you wanted to do. Because, I mean, I have Adam here. He has been doing solvers for the refraction game, right? You could do things like that, you know, digging a path from A to B with other algorithms. And I was wondering if you have some sort of baseline sort of to compare with against the GAN.
Yeah, that's a very good point. And actually, there was a reason for choosing GAN. We unfortunately we haven't done like any other baselines yet, but we in the future we wanted other school teacher or education collaborator to create this kind of levels to give the students. So we wanted to have the model that could learn the distribution from the model. So we thought GAN would be the good start to start with, but because we haven't done any other experiment for other machine learning method yet, so that's the good way to go, I think.
Oh, another question up there. Okay, there is one there. So you asked the answer like.
In the example level you showed, there were actually 2 points from what I saw where you could input code while you actually only needed 1. does that mean that some of the levels can be revisited maybe in reversed order? Or is there a specific reason why there were 2 points, even though you didn't actually need it?
Sorry, can you repeat that?
Okay, the practice level, with the video you showed, the character walks to a point on the wall, some disk, and I actually saw the same disk at the opposite side of the room near the door, and it was also present on the diagram you showed, even though that second disk actually wasn't needed at all, because you could, well, I'm assuming here you could immediately leave the room and it would be considered puzzle solved. So why the second disk?
So in the Engage game, all the device has its own pairing point. So the first one that student pair is for the moving platform that they have to move. But the second one is for opening the door, actually. So that is the read-only program. So if they pair it and if they execute it, it's just open. So it's not like asking them require the programming stuff. So so I cut that part from the video. So I just wanted to have like the moving platform part for our variation in the author levels, if that answers.
Okay, the question here.
Yeah, thank you for your presentation. I know a couple of your authors, co-authors, have been the authors also of the deep stealth approach. Are you aware of that?
Deep stealth?
Yeah?
Yeah.
So is your research, this research somehow connected to deep stealth? Is it deep stealth with just level generation on top of it, or is it something completely different that I don't get? I mean, your student model instead of competency model, and we don't have a clarity of the statistical models that you use, but
So I have a very shallow knowledge about the deep stealth. So it's for providing adaptive scaffolding. It's like giving students hints or the feedback of what they're doing. But here in this work, we wanted to actually generate the level that student can solve so they can master the concepts themselves.
Okay, the last short question.
So with this solution, you use the solver as an external element to feed into the second stage of the GAN. Would it be possible to integrate the solver into the discriminator to increase the solvability of generated levels?
That's a very interesting point, and I honestly haven't thought about that. But that's worth looking into it and compare which way is the good way to.
I'm Chiara and I'm from Maastricht University, and today I will try to convince you that sometimes it's actually a good idea to randomize the parameters that control the search when playing games. In this case, we're focusing on Monte-Carlo tree search. Let me start with a few words on the test domain that we're using. So we're testing randomization of parameters in general game playing, which aims at creating agents that can play many arbitrary games that the agent might have never seen before, and the rules are given to the agent only at runtime. In this case, we're focusing on mostly abstract games and board games like chess, checkers, and so on. And general game playing comes with a lot of challenges, among which the fact that the agents have no game-specific knowledge that they can exploit. They usually have a very limited amount of time to choose moves, normally a few seconds per move. And they require online learning to be able to do anything, because they cannot learn anything in advance if they don't know which game they're going to play. An approach that has been quite successful in general game playing is Monte-Carlo tree search. You're probably familiar with this picture by now. So I'm not going to spend too much time on that. Basically, Monte-Carlo tree search builds a tree representation of the space of the game, of the search space of the game, incrementally. So repeating the 4 phases that you see there on the slide. And what I want you to notice is that there are a lot of strategies that are normally used in Monte-Carlo research in the selection or in the playout phase, and there are also a lot of parameters involved that control how this tree is built and visited. And if you're familiar with literature on general gameplay, what we usually see is that it's very hard to find parameter values that are good on every game. Normally what we see in papers is that they try a few parameters and they stick to one that is performing overall best, but there's always some game for which is optimal and some game for which the parameter values perform badly or not optimally. So this brings me to some previous work that we did. In our previous work, we tried to tune the parameters online. So when we play a game, we try to adapt the parameter values while playing the game. We basically use each Monte Carlo simulation to evaluate a different combination of parameters, and then we use the reward that we get from the simulation to adjust, to decide basically which other parameters to visit next, trying to exploit good parameter values, but still explore other combination of parameters that we have seen less. And what we've seen from this is that the performance on some games improves when we tune the parameters online. And this brings me to the motivation for this work. So why are we interested in randomizing the parameters if we figured out that tuning them online, it's usually working? Well, what we wanted to see is what if part of the reason for the improvement that we get is not that we're intelligently choosing the parameters, but that we're actually not keeping them fixed. So this repeatedly changing the parameter values might help diversify the search. And to test whether this is true or not, we can just randomize them and see if we get any improvement at all. Moreover, we didn't come up with this randomization out of nowhere. We've seen some related work in the literature where adding randomization to the search is actually improving it. Starting from the work of Bill in 1994, he basically he showed that adding a random term to an evaluation, a state evaluation function, was actually improving the quality of play in chess, because this random term was able to capture some structure of the tree that otherwise would be ignored, indirectly capture this structure. Another example is the work of Bozanski. They basically use a random tie-breaking rule to choose an action when they have multiple actions that have the same value or that have very similar high value, instead of always picking the same one with the highest value. And they get some good results with this, adding this rule in, I think it was 6 simultaneous move games. And finally, we also found the work of Chen, which is probably the most similar to what I'm going to show you next. And what he does, he basically randomizes some parameters that control the selection strategy of MCTS, and he also tries to hierarchically randomize different move generators in the playout phase of MCTS. And he shows that this randomization helps diversify the search and improve the performance in some circumstances on the game of Go. So how are we implementing this randomization in MCTS? Well, it's pretty trivial. We just select the parameters that we want to randomize that control the search. For each of them, we select a finite set. We're doing this manually, so we manually select a finite set of values that are sensible for the parameter. And then we use a randomization strategy to change these parameters online. We are comparing 4 randomization strategies. The first one is randomizing per game run. So we're basically just keeping the parameter fixed for the whole run of the game, but we just select them randomly at the beginning. So for each turn, we would run MCTS with this random combination of parameters, select an action, run another MCTS search, and so on. The second strategy is randomizing per turn. So before running the search for a turn in the game, we randomize the parameters again. So we would have random parameters, MCTS, select an action, randomize again, and so on. Then we're going to a more fine-grained level where we randomize the parameters for each simulation of MCTS. So we would randomize the parameters at the beginning, perform a simulation, and then randomize them again before performing the next simulation. And finally, we're going to randomize the parameters per game state. So whenever we visit a state, we randomize the parameters that we are using in that state to select an action. And we do this for each state that we're visiting in the simulation. So how are we evaluating these strategies? Where we use a baseline agent that is MCTS based, but we enhance it with the G-rate selection strategy and the must playout strategy. For those of you that are not familiar with these strategies, in short, what they're basically doing, they try to balance exploration of less visited move and exploitation of good actions, adding a bias towards the actions that have been performing well, generally well, during the game simulated so far. Here is, I reported the parameters that we chose. You don't need to know exactly what they do, but it's just to give you an idea. We have 6 parameters in total, and for each of them we identified a set of from 8 to 9 values that are sensible for the parameter. And they're all, in one way or another, controlling how the actions are selected during the search. And in bold, you see the values that we actually selected as the generally optimal ones that we're using as the comparison when we randomize. This is the set of game on which we're performing the experiments. We try to pick an heterogeneous set of games, so we have 2-player games, 3-player games, some simultaneous move, and some with sequential moves. And the first experiment that we performed is comparing the randomization strategies against each other. We're testing on all the 14 games. We use 1 second start clock and 1 second play clock. So for each turn of the game, we give 1 second to the player to think. 500 runs of the game are performed for each game and for each pair of agents that are matched against each other. So first of all, we have performed a round-robin tournament for using different number of parameters that are randomized. So we try randomizing only 2 parameters, 4, or all the 6 of them. And we match against each other the agents that use all the previously mentioned randomization strategies. And what we've seen is that randomizing per simulation is the strategy that is achieving the highest win rate on most of the tested game, with randomizing per state being the second best one. To further compare them, we matched these agents against the agent that is not randomizing the parameters, but is keeping the fixed values that I mentioned before. And once again, we have the confirmation that randomizing per simulation is performing best among all the simulation strategies. But you probably all have noticed that none of the agents is actually better than the agent with fixed parameter values. So I'm not very good at convincing you so far. But I have nicer results in the next slide. So what we tried to do is we picked 3 parameters out of the 6. We selected the parameters that seem to have the highest influence on the search. And for each of them, we consider 1 agent for each feasible value, and the agent that is actually randomizing the value of the parameter among all the feasible ones. We matched, for each parameter, we matched them all against each other, and we've seen something interesting. Here I'm just reporting some examples of the results because I don't have time nor space to show them all. But there are some games where randomizing is actually performing better than any of the fixed values. So you see the randomization on the right has a win rate that is the best over all the possible parameters. In bold, by the way, is the performance of the parameters that we're using as default. This is not true in all games. We also have games where randomizing is not the best, but is still better than the parameter that we selected as the generally optimal one. So if we don't know which parameter is, if our optimal parameter, generally optimal parameter is not always optimal for all games, then randomizing is still better. And then we also have this other type of games where randomizing is not better, is not the best, is not better than the default value, but is still better than a few of the values. So if we really don't know which one is the best value, randomizing is still better than risking to use a suboptimal value for the parameter. Next thing that we tested was, well, we tuned the parameters online before, so how does this compare with the randomization of parameters? In the slide you can see we compare the two agents, matching them against the agent with default values. And you see on the slide the overall result over all the 14 games. So we see that for two parameters, randomizing or tuning online has more or less the same performance and is also almost the same as keeping the parameters fixed. For 4 parameters, their difference gets higher because tuning seems still to be better than randomizing, but when the parameters become too many, in this case 6, online tuning is way more difficult to achieve. So randomizing has more or less the same performance with less computational cost. But more interesting than just looking at the overall performance is to look at a few of the games, because if we pick only some of the games, we actually see that there are some games where randomizing is much better than tuning online and also much better than keeping the parameters fixed. So in Quad and Connect 4, we have in Quad we have more than 70% win rate, and in Connect 4 random gets like around 55. But at the same time, we also have games where the situation is switched. So online tuning is much better than randomizing. And we see this in Night Through and Breakthrough. And we wonder why. Why does this happen? Why is sometimes one is good and sometimes the other is good? So we looked actually at how the tree is built by all these strategies. So using default parameters and keeping them fixed, randomizing them or tuning them online. And we just looked at a few trees, and I have some examples here for the game of Quad. And what we notice is that with default parameters, the tree that is built, by the way, every step has a different shade of gray every turn in the game. With the default parameters, the tree is very narrow and deep. So it tends to visit the tree deeper, but not explore too much in too many branches. Where randomizing does the opposite. It tends to be shallow and build a much larger tree, but go less deep for each turn. And online tuning seems to be sort of in between. And this actually happens for all the games that we've tested. We have the similar situation in Connect 4, in Night Through, and in Breakthrough. So this performance seems to be very much game dependent. So this brings me to the conclusions. We've seen so far that for some games it's better to randomize the search control parameters rather than keeping them fixed. Parameter randomization is also beneficial for games where the fixed parameter settings might be suboptimal. Parameter randomization is also a valid alternative to online parameter tuning when the number of parameters gets too high and we have a limited search time. And finally, whether it's better to tune or randomize is very much game dependent. So as future work, it would be very interesting to be able, for each game, to figure out whether it's better to randomize, to keep the default fixed parameters, or tune them online. And also which and how many of the parameters we should randomize or tune. It would also be interesting to continue to further investigate and analyze how the trees look like and get more statistics about how the branches are visited, how deep they're visited, how many times. And this concludes my talk. Thank you very much for your attention.
Perfect timing. 5 minutes for questions. Anybody?
Hi, thank you very much for your talk. I was wondering, have you considered if this could also be an indicator if Monte-Carlo tree search is like a good approach at all to use in that game? So we've, I think, seen in some of the GVGI versus algorithms tables that a breadth-first search sometimes outperforms MCTS. And maybe this could be like a way to also detect something like that.
Yeah, definitely. One of the first things I thought when I saw random doing so well on a few games, I thought that maybe it's not very smart to try and make the playout smarter, for example. If random is, like visiting the tree more randomly is better than trying to do something smarter and exploring, focusing too much on certain actions. That might indicate that MCTS with his focus, MCTS is famous for focusing on good actions, might not be the best option for those games.
Chiara, thanks for your talk. I guess it's slide 10. you compare the overall performance with just on some games. The overall was decreasing as the amount of parameters increases, right?
Mm-hmm.
The amount of wins, yeah, exactly. I was wondering in those in quad, in the middle upper, why is the amount of wins increasing with the amount of parameters you're randomizing? Is pretty much the only one. Is there an easy explanation for this?
My guess is that in quad is, well, the more parameters I'm randomizing, the more the search is diversified. So the more the tree is visited randomly.
But this explanation holds for all games in general.
But
so why is it working better in wins?
And I guess that in quad, it's actually, there's no like single strategy. You can win with many different strategies. And when MCTS is trying to focus, it just finds one. If you diversify, well, I don't know if you're familiar with quad or have you, okay. So basically what you have to do is you have blocks and you have to place them on the board so that when they're connected, they form a square. But it could be straight square or like diagonal. And then you have other blocks that you can use to block your opponent from building this square. And intuitively, if you can imagine, this game would have many solutions. And when you're winning with just one move, your opponent can actually block you. But then with another move, you might open a lot of other possibilities. And I guess that the more parameters I'm randomizing, the more random paths I'm exploring, and the more I'm finding all these possibilities. So, that's my guess on why it works on this game. While Night Through and Breakthrough, they have very narrow win paths.
There's time for one more.
Can you just go back to the slide where you have all the bar graphs on? So just one question. Are you sure that if you didn't do a finer grained search over the actual parameters, the randomization wouldn't just match some sort of intermediate bar there?
No, I'm not sure. Okay. Well, I try to pick sensible values, but you're right, I'm not checking what's in between.
Okay, let's thank Chiara again. So the next presenters are Corinna, Jaschek, and Tom Beckmann.
All right. So we're going to talk about mysterious murder and MCTS-driven murder mystery generation. So when we think about murder mystery in games, we think about maybe games like L.A. Noire, where you kind of, it takes you by the hand and leads you through the storyline, and you can make assumptions, you can accuse people, but kind of no matter what you do, at the end, you'll get to the end of the storyline, and you would have find out who the murderer is. In contrast to this, our earlier games, Murder on the Mississippi, where you really need to collect all the evidence on your own, and if you miss a final piece, then maybe in the end you can't solve it, even though you went through the whole game. And the Shiva is kind of an in-between, where you can collect evidence, and you can never miss evidence, but you still have to figure it out together to have to find out who the murderer is. But all of these games have in common that they're fairly linear and there's little to no branching. So once you've played them once, there's really few reasons to do so again. So we wanted to do more something that you can play again. So we went into the direction of procedural narrative generation. And two examples we were inspired by are Facade and Prom Week. So Facade, in Facade, the story is generated by different events that may or may not happen each time you play. And depending on your choices that you make, different events happen and a new storyline emerges each time. In Prom Week, the story emerges by you interacting with characters, so they act according to their social norms, and depending on what choices you make, a storyline will emerge there while you try to find a date for prom. But both of these still have in common that there's a lot, like months or even years, of humans that wrote these events or that wrote these social interactions, before you can come to a game. And we kind of try to keep that human authorship down and see if we can still generate interesting stories. So here's a quick demo of what we did in the end. So this is kind of like an Agatha Christie style locked room mystery. So you have 4 characters, one of whom is the victim, and 3 suspects. And you can now go about questioning suspects, ask them maybe about their mood, how they're feeling. So this person seems very happy, which might already be suspicious, and you can ask what kind of possessions they have, so you can search them. So, as a weapon, so. But you can also ask them about other characters. So you can ask about their relationship to this character, so they seem to be related in some way, and their feelings about this character, and he seems to be angry. And we introduced another system, which is basically a witnessing principle. So every time during the generation of the story, a character chooses an action, there's a tiny chance that another character witnesses this. So now you can kind of make the characters incriminate each other. So in this case, he paid off a debt to someone. And in the end, you can, if you think you know who did it, you can make an accusation, and it turns out we were wrong. No, you're right.
Yes, you're right.
So in our user interface, we kind of tried to use as little text as possible and relying mostly on emoji. And this is kind of cool because it lets us recognize characters really easily. You don't have to necessarily even remember all names, but you can just see on one glance who is who. And it also kind of helps this emergence of story elements. So maybe you already made up your own mind why 2 royal guards and a child murdered a scientist. And it also kind of keeps this authorship factor low. We don't need to write text for each event or maybe even different texts, but we kind of let the specifics of the story in the player's head so they can kind of imagine their own story. And this worked really well as long as we were trying to represent emotions and relationships, because this is kind of what they were meant to do. But it worked less well when it comes to the rules. For example, we have rules for stealing and paying someone money, and these are kind of both represented by money. And that's obviously not ideal if you can't say if someone stole or gave someone money in a legitimate way.
Let's look at the things that are underneath the system, in particular Scepter, which is a prototyping language by Chris Martins for procedural narratives. At its core, it has linear logic, which I want to explain here really quick. So in classic logic, if you are in possession of a pound, you know it to be able to acquire a lollipop for that. And you also know that given that pound, you can acquire cake. And classic logic would let you to conclude that given that pound, you could acquire both a lollipop and a cake, which in practice is somewhat unrealistic. So linear logic addresses this issue by thinking in statements in terms of resources. So rather than saying these are general truths, you are exchanging the left-hand side of the expression by the right-hand side. So in this case, I'm expressing an exchange for the pound for either a lollipop or a cake. What Scepter does at its core is keeping a state of predicates, like here in this example where John and Eve like each other, but John is also quite angry at Eve, and he is in possession of a weapon. So following with our murder mystery style, we can now add a rule to this. For example, a stabbing rule, wherein given a character that is very angry at another and in possession of a weapon, they can stab the other person, leading to a new state I1, wherein Eve is now dead, John still in possession of a weapon, but he's no longer angry, so that's something. This is how it looks like in practice for us. Like on the right side, for example, you can see the scientist being angry at the girl, the two of them fighting. As a consequence of that, this generates new resources you can see below. In this case, even more resources, and apparently in this particular run of the story, this actually led the girl to kill the scientist because she was so angry at her. Now, we took Scepter. What I described so far is essentially the baseline system that already existed, and we quickly realized that we would have to rewrite it because the standard meta language in which it was implemented was not meeting our performance requirements. We first rewrote it in Python and then later in Rust. While doing so, we took out some of the advanced features that Scepter has, namely types and inheritance and stages, because we did not need them for our specific game. But what we added is this MCTS agent that I'll elaborate on in a second, to enable us to have autonomous agents acting intelligently, because previously you only had random playthroughs or interactive playthroughs where the player actually took each single step along the way. We also added non-deterministic outcomes and a templating language. Now, just a rough breakdown of what the system consists of, mostly those 4 blocks, where the simulation processes the actor and the predicate state. It can pass a copy to it to the MCTS subsystem. It will just ask the linear logic evaluator, given that action, what is the score I'm expecting for this? It will report back. The MCTS system does its thing, as we've just seen on the slide again. And finally report back the most promising action, which the simulation can then apply to its canonical copy of the actor and predicate state. Now, the way we implemented the MCTS system was based on the 3 scores, loosely based on Maslow's hierarchy of needs, the top 3 layers in particular. So if you take this farmer, for example, he can propose marriage to someone else, give him a couple of preconditions. And you can see in red and in green 2 different outcomes of this action, each with a percentage of 90% success, when the sanity and social scores would increase, but a 10% chance of failure, when the sanity and social scores would decrease, and he becoming angry at that other person in response to that. We specifically implemented our MCTS system with very few look-ahead steps, and in a way that once it expanded a single node that is non-deterministic, it will save that outcome, which in our limited testing admittedly led to actors sometimes taking suboptimal decisions, acting overly confident or somewhat short-sighted, which we found to be a great fit for this type of game, where wrong decisions can lead to interesting outcomes. The most important part of all this was designing motivations in such a way that the player can really see the thread going through the story and making sense of it after the fact. In particular, this means that we had to introduce certain global preconditions, such as actors being alive, which before we did that, we occasionally had zombies revenging their own deaths after being killed, which we obviously don't want. We also made sure that rules try to balance each other to delay the inevitable, such as two actors fighting with one another creates anger resources that can be then consumed again by the actors making up, prolonging the story and making it a bit more interesting. However, we still bias the overall rule set towards escalation by providing especially high scores for murder or stealing action, which create the dissonance in the simulation. To give the characters more character, we decided on adapting 3 systems. The most simple of those is an alignment system, like you find it in many role-playing games, whereas an evil character might just be able to start stealing things, whereas a good character would maybe have to be in dire need of paying off a debt. Additionally, we took the big 5 personality traits to make the characters tend to certain decisions more likely, and we took the Plutchik's Wheel of Emotion to model the emotions between different characters if they're angry, for example. Quick tidbits on performance, because this was like one of the main things we had to invest a lot of time in. We started out with hashing and tried to figure out how we can get this to run fast enough for the MCTS to get enough sense of the simulation. And at some point we realized we can actually fit the whole state into the single hash by bit shifting the things together and making the rule name that we would otherwise have to keep a lookup, and then adding the up to 3 actors just behind it. So this gives us options of only rules that include 4 characters per predicate, but would allow up to 256 different characters and 2 to the power of 30 predicate names. So well within the limits of what we actually had. We ended up at about 30 rules that we actually refined. Now, while we are also the system, both of us not having a background in narratives, we found that the rules that we defined were rather limited to really introduce complex stories. However, we did notice that even for us, defining these rules was rather fun and direct. Only occasionally we had troubles with ensuring manual consistency, like as I mentioned, we always had to put this alive statement everywhere to make sure dead characters didn't go crazy. And we could also not currently test for the absence of a resource, so we also had to ensure manual consistency there. However, we had some limited playtesting with colleagues and some friends, and we did really notice how especially the emojis got this emerging idea going. And most of the time, this planning behavior also made sense, where you could see, okay, these characters were angry at one another. This is probably some sort of indication. So to conclude, we think this is a good step towards reducing a lot of authorship, but we also really noticed how we would need a professional author to sit there and check, does this really work in a larger context? So what we imagine as next steps, most evidently trying out just this. Additionally, we had a lot of thoughts about the game itself, like aspects like information hiding and finding contradictions within testimonies. We thought was quite a promising direction. So making this game more like a narrative puzzle. Additionally, an interesting thought we had was having a collaborative web editor for rules where crowdsourced basically we would get a lot of diversity in these rules. And since this is actually a system made for interactivity, it was actually a shame that we just cut it off at the very point where it got the most interesting after the murder. We could very well imagine letting a second stage of rules go on with the same characters, where the player suddenly, as the detective, takes an active role in the game and starts questioning the other characters. All right, thank you.
Thank you very much. Questions?
Very cool stuff, thank you for showing that. What kind of reactions did you get from your test people? I mean, I guess you test played it to see if all these concepts play together. Mm-hmm. So could you relate a bit what they told you?
Yeah, it was a bit of what I already touched upon, and we did not get that much data.
But you test played it yourself, I guess. I
Sorry?
mean, you are several people, so you test played it yourself. So what did you think about it?
I think, especially, so we had this feature where after you kind of said who did it, you can look at the graph of these are all the actions that kind of happened. And once we started looking around that, there was nearly always like some sort of logical and maybe even kind of funny narrative, which I think doesn't really come across much yet in the game. But I think, yeah, there's definitely potential there, and you can really infer a lot of stories from even very short graphs.
Yeah, thanks very much. Is that available, actually? Can I play that on the web? Or?
Yeah,
almost, yeah.
Almost.
The Rust version is web compatible. We're just finishing the UI off right now. Yeah, the link, if you follow it, then...
You can already like get the code downloaded and use the Python version, so...
Yeah.
Thank you, Diego. This is really interesting, and I'm going to try it out as soon as it runs. I had a question about evaluation. So you have this graph, which is really convenient, the SVG that you showed before. Mm-hmm. Maybe one way to test this with your users would be to have them identify which of these parts they understood. So which of these, which parts of these contingencies they actually figured out by interrogating people. Because it's easy to just go like, I found the knife, so it's easy. Mm-hmm. But whether you understood, oh, this is because this happened and because this happened.
Yeah, very good point. Mm-hmm.
So in some of the work in computational models and narrative, they look at how you might generate a story by having characters kind of simulate, and you have this notion of emergent narrative occurring. And in other approaches, you kind of plan out a story more from like an authorial goals, or how you want to achieve a good narrative. And I wonder, with the approach you're presenting here, where do you see this fitting more in that kind of constraints? Is it more kind of an emergent type thing, or is it a planful narrative generation from an author perspective?
Yeah, I think we are falling a bit on the middle in that spectrum, because we are, while having the strong root in emergence, We are also having some means installed that make sure that the stories become succinct and end up with a murder rather quickly, and various means to increase the tension between the different rules. Whether this works as well as we're hoping it, as I said, the evaluation is quite early, but I would say this is about that area.
There is time for more.
Hello, thank you for your presentation. Most of the mystery type of narratives that we see in both games, movies, or even literature usually become good because they have the element of surprise to it. There are things that the reader or the player doesn't know and actually have these kind of aha moments where a new kind of evidence show up, and then maybe it's misleading, and then it goes around the loop, and then kind of comes to a conclusion. So, how do you incorporate this element in your design?
So one of the features that we kind of planned less for the story generation, but more for the game aspect, was to let players or let the murderer lie about what he did, and currently they just always admit to having a weapon. So I think if we were to give a chance for them to falsify their testaments or to hide some things, then you'd make it a lot harder for you to figure out, and maybe if you find contradictions in the statement, that would kind of lead to this aha moment, like, aha, you had lied to me, so therefore I think you did it. Yeah.
Okay, let's thank the speakers again. So our last speaker is Mike Cook.
Hi everyone, my name is Mike. I hope you all can hear me okay. And I've been looking forward to giving this presentation for months and months and months. This is work that I did at the Max Planck Institute for Software Systems with my colleague Azalea Raad. And a lot of it comes down to, this is our academic power pose, sorry, I introduced just very briefly. This is about the field that I primarily work in, which is automated game design. I build AI that design games or help people design games. And often this is from, like, I'm interested in the kind of esoteric, social, and cultural aspects of this. But really the whole problem area is extremely tricky. And one of the key questions, obviously, is what is it that makes a game good? Whatever good might mean to you, what is that word doing when we talk about games? And lots of people have tried many different ways of answering this question. So, for example, one thing that we could do is get agents to play the game and then see how they do. Maybe better agents should perform worse agents at a game. That means that it's strategic or there's skill involved in playing it. Julian Tegelis and Jürgen Schmidhuber had a great paper on that, for example. Or maybe we can learn from other game designers examples of what makes a game good, or how to solve certain design problems and apply that. Thinking of work by Daniel Caravalos there. Or maybe we don't actually need to play the games. Maybe we can do things like look at the rules and think about what the consequences of these rules are and think about what they imply. And you've got things like Cygnus there. And I've kind of dabbled in most of this at some point, and they're all useful, they all have their own strengths, but there are also drawbacks in there as well. And a lot of it really comes down to how we answer this question, right? We want to know what happens in a game, as much as possible about what happens. And traditionally, when we want to do this kind of thing, we build state space graphs, or some kind of graph representing things that can happen. So a game state is, a snapshot of what is happening in the game at this moment. It might be very detailed, it might be kind of more high level. And then the vertices that come out of these states represent actions that we take, either literal ones, like pressing the Z button in Spelunky, which makes you jump, or it might be more kind of in fiction things like the word jump, or dropping a bomb which might cause the bomb to explode and transition you to a state where you're not alive anymore, the game is over. Now, the thing with state space graphs is that they're typically partial, okay? Obviously, they're partial, right? And we've seen lots of examples, like this diagram, everyone's favorite, of state space graphs that we construct to do things like play games using MCTS. And partial state space graphs make a lot of sense, right? Because that's all that we need when we're playing games, especially when we're doing things like selecting the next best possible move that I could take, for example. We don't need to know every single thing that could possibly happen in this game ever. That would be ludicrous. So the problem is that this approach, as a designer, like as a player, that's great. You just want to think about like what's the best move I could take right now, not what would happen if I charged all of my pawns in a straight line across the chessboard. But as a game designer, it doesn't tell us much about what can go on in a game, right? So we have this state space that's like showing us routes that end in certain outcomes. But what we don't know is what's happening in the choices that aren't being taken, the paths not traveled, right? And really, what we would like is to be able to see everything that's going on, right? That would be the dream. And then we'd be able to see all of these strange things that can happen. We wouldn't just know what the next best move is. We would know how likely is it that we would pick that move given certain other conditions, or what is the worst thing that could happen, and how often would that worst thing come about. Ideally, we would find out every single possible thing that could ever happen, ever. And in some cases, we've done that. So like for checkers, someone actually did that. They spent, I think it was 15 years computing every single possible state a checkers board could end up in. Fantastic. I love it. Obviously, most people are not going to do this. And the reason is that it's just really difficult. These things are massive. And even for a simple game, like this is one of my favorite games ever, A Good Snowman is hard to build. Even a game like this, where you're just rolling balls of snow to build snowmen, these things get quite big. And for some games, I'm thinking games like Civilization, for example, these things can be infinite. You never need to stop playing Civilization. The state space graph goes on forever. So, exactly, literally. And it actually gets worse than this. So in board games, there's a lot of impact in every single move you make, particularly in multiplayer board games. But video games tend to do the opposite. They tend to dilute the impact of actions. So if you think about a game like Soccer Band, this is a Soccer Band-like that I've smashed together with some art that I didn't do. But you push boxes around and you can move around a grid, right? So if I want to move to this square up here, if I was playing a board game, I might actually just pick the little man up and put him in the corner. But in a video game, I press up, right, right, right. You know, I've got all of these small actions that add up to a meaningful action that has intent and relevance, but it's broken down into these very ambiguous, granular, small decisions. And when you think about a game like Breath of the Wild, right, this is even more obvious. If I walk to the other side of the map to do something, all of these things happen on the way there. All of these actions, and no single action represents wanting to reach, you know, the top of that mountain in the distance. It's all messed up and diluted and mixed in together with actions that actually don't have anything to do with reaching the mountain, as well as ones that do, but it's unclear why, right? So this is a nasty problem. So how do people normally solve it? Well, if you look at, for instance, when people are writing an AI to play a game like Soccer Band, we use our knowledge of the game, right? And one of the great things about these conferences is you meet someone who loves Hanabi, they know Hanabi inside out, and they can use their expert knowledge to build a better Hanabi player. And I love that about this conference. So, for instance, if you look at papers that write Soccer Band solvers, instead of moving the person around, because that's a very diluted kind of action, many of them will use their expert knowledge to instead build an AI that essentially moves boxes around, because the boxes are the important part of Soccer Band. You need to get them to goals. And yes, you have to, you know, move the person around to push the boxes, but that's too much for an AI to do. It's much better if we focus on the meaningful actions. But for generated games, there is no expert. In fact, no one's seen this game before. And so you have no idea what a heuristic might be. You have no idea what is relevant or important. Anything could be important. Nothing could be important. It could be an unplayable game for all you know. And so it's really hard to know what things to miss out, what things to combine. And although I'm talking about automated game design here, in the paper we mention other cases where this is relevant. So I'm sure many of you are interested in GVG, like general game playing. It's obviously very relevant there. You've not seen this game before. And even in things like co-creative design tools, if your player is designing a game in front of you, you've never seen this game before, but you've just got to go along with it. You've got like half a second to figure out how to play along with whatever the user is doing. Mario Maker is obviously not a game designer per se, but it's very good at saying yes and. But as soon as you get into rules, it's way harder. So, it gets worse. The other thing that we can't do is compare Sokoban to Super Mario. And one of the reasons for that is when we use compression to break down a state space, we also fundamentally change like what a state means or what a transition means. And we start like mixing things together or changing terms or introducing new ways of describing things, like Sokoban focusing on moving the boxes. Now, most of the time that's fine because most people don't want to compare Sokoban to Super Mario. But in automated game design, it's actually really handy to say, what is the difference between this game I made and this one that I made yesterday? And if we're using compression techniques to melt this one down that's unique, then suddenly these state spaces aren't comparable anymore. So what we'd really love is a way to compress state spaces so we could get as much knowledge as possible without losing any important information and having no upfront expert knowledge whatsoever. That's what we would like. And today, I'm going to tell you about one weird trick that I discovered that lets us get maybe a little bit closer towards that. And it relies on this thing that I call reversibility. So we're playing Sokoban, and this is our game state, where we're standing next to the box. It's a really tense moment in the game, and I press the down key, and I move down. And I enter this new game state, G2. And then this is obviously also brimming with tension. And at this point, I press the up arrow, and I move back up, and I'm standing next to the box again. And I'm in this state G3. And we call the action of moving down, or indeed the action of moving up, we call it reversible if we can say G1 and G3 are equal, according to this equality operator, right? And what does this mean? Well, in the paper we go into more nuance, but for now, I want you to imagine that this equality operator is extremely strict. It means that two states are equal if every single possible piece of data that could affect the execution of the game in any way are all equal in both states, right? So this is very aggressive. But that's what we use, and so I want you to imagine that for the rest of this talk. Now, if I push the box by moving right, this is not immediately reversible, because if I press left, I will be standing on my own next to an empty space, the box won't have moved. But it is eventually reversible. There is a chain of actions that will push the box back and get me back to where I was. So if there is some sequence of actions that leads to a state which is equal to my starting state, we call that action eventually reversible. Oh my lord. No, we're okay. So that's immediate reversibility and eventual reversibility. And here's where hyperstates come in. I know this sounds like we're just getting started, but I wanted to give you lots of motivation, so don't worry. If two states are connected by reversible actions, they can be combined into what we call a hyperstate. We effectively say they are the same state, because we can get out from one state to another and back again without affecting the game permanently. And of course, we can do the same for eventually reversible states as well. If a state is in a chain of eventually reversible actions, they combine together. And we can actually iteratively grow this out. And I actually have an algorithm that doesn't mean we have to generate everything at once. We can actually slowly grow these nice hyperstate graphs. And if you want to see something pulled directly from the paper, what you can see here in the top left is a regular state space graph. And the thing I've ringed in the solid red line, those are regular states that are in a cycle, and you can see in the bottom right they've been combined into one big hyperstate, right? So the bottom right diagram is simpler, it only has 6 states, okay? And that's a hyperstate space graph. So here's some interesting things about hyperstates. First of all, they align very closely with what people use as expert heuristics when they write AI papers. So for instance, this Sokoban thing is very close to the intuitive notion of what it means to have reversible and irreversible actions in Sokoban. And you may have seen the Monte-Carlo 2 presentation, or is it tomorrow? No? Yes. And last year I came across Monte-Carlo 1, and in the paper they talk about removing actions which would not have an effect on the game. And we see this in many cases, and we mention this in the paper. Like, it's really interesting where it echoes expert attempts to reduce game state spaces. It also allows us to concisely represent certain kinds of game design theory. So in particular, strategic headroom is one of the ones I use in the paper, which is from one of the NetHack designers. And there's a really nice way to express it using hyperstates. So that's the stuff that's in the paper. And the paper's really about presenting the idea of hyperstates to you in a clear, clean, and formal way. But just for you today, I have some bonus material that I couldn't fit in the paper, and I've been wanting to tell people about. So here's a soccer band level. It's taken from this big database of soccer band levels, and it's an easy one, which means the solution is only 17 moves long. Now, if you look at every possible state the game could be in with 17 moves, you will find that there are 716 unique states. If you compress this with hyperstates, you get 50 hyperstates. And if you remove all of the hyperstates from which you can never win the game, this level compresses to 5 hyperstates. And those hyperstates kind of represent the meaningful stages of a solution to this level. It's really wonderful. This is a game which was co-designed with me and my AI game designer. It's called Before Venturing Forth. And due to it misunderstanding my rule set, you can move all of these adventurers at once, and you have to get as many as are alive to the exit, basically. So the one on the left, this level was made by the system, takes 5 moves to solve. One on the right has 10 moves. So here are some interesting things about this level. The root hyperstate, the one you start in, on the one on the left has 21 game states compressed inside it, because there's so much you can do at the beginning without affecting the game permanently. Whereas the one on the right has a single game state in it, because as soon as you do something, you branch the game permanently and you can't go back. Similarly, the average size of a hyperstate on the winning path in the left one, it has 8 game states in. So this is very chunky, there's lots of breathing room, there's lots of stuff that you can, there's lots of times to think about what you're going to do next. Again, the one on the right, the average size is 1. It did not compress very much. And it won't surprise you if I tell you that the level on the right is considered to be harder. But I'll mention in future work, I think these actually tell us why they're hard. It tells us the type of difficulty they contain within them. So, future work. I promised I was getting towards the end. The first thing is that I think hyperstate space graphs will actually build really interesting tools for game design. So here, each one of these game screenshots, they represent a hyperstate. And this is what I'm telling you, this is what I meant when I said that soccer band level kind of tells you the steps towards a solution. So don't worry about interpreting this right now, but I can always show you something on the laptop tomorrow. These are actually really nice condensations of each of these puzzles, and it's really satisfying to look at them and see how they lead to solutions. In the paper, we also deal with how to apply the idea of reversibility to real-time games, but it's definitely future work. It's going to be a big one. I'm not even sure if I can stomach doing it. And finally, this is the thing I'm really interested in. Does the texture, the way in which a level compresses and a rule set compresses, does that tell us something about the nature of the challenge? We often record how difficult something is, but I want to know why it's difficult. Is it difficult because you're overwhelmed with decisions, or because there's 2 decisions but you can't tell which one you should take? And I'm really interested in that as well. And I have some comments and stuff and secret stuff. But in the interest of wrapping up, thank you so much for listening. I'm sorry it was a bit breathless. Here's where you can hear more from me and Azalea, and thank you so much for listening.
So, since I'm in math, I'd say what you're doing is taking an equivalence relation, but a really useful one, and imposing it on the state space. And the question I have, is it easier to build it up incrementally, compressing when you can, or to pull out all the states and then compress?
So something I'd love to do at this point that I couldn't do in the talk is shout out Nathan Sturtevant, who really inspired me by making this paper about exhaustively generating all game content, which was great fun. And I like that as well. So one of the problems is that sometimes, I like that as well, but sometimes these problems get massive. So I wanted to do the iterative solution because I felt like that was the responsible thing to do, because people would want, the first question would be, can you do this more efficiently? So I thought, I'll just do it now. But yes, I'm into that too, definitely. Yeah.
I actually had almost the same question, or a quite similar question, because in area of formal verification, when basically state space is explained also symbolically, there's the construction of the binary decision diagrams, or potentially even multi-value decision diagrams, where basically the actions that system can take then get to represent the symbolic states, and the construction, because exactly of the state space explosion, is progressive, because you could never create the whole state space that you need to verify. So I was curious if you considered actually looking into the formal verification and constructing the decision diagrams, because the amount of actions, for example, for Socobond is very limited, and the construction could be actually easy to do using the tools that maybe we have 20 years already.
So Azalea actually works in formal verification, and funnily enough, after we wrote this paper, a colleague in her group started working on that kind of thing, and we were very interested in it. And I am interested in it. one of the things I like about this is that it's quite simple and easy to apply. And the other thing I think about is like, how would I put this, like a tutorial for this on itch.io for indie devs to learn, that kind of thing. So I am interested in it, and we hope to explore it. But also I want to make sure that I'm a sucker for like simplicity as well, so I would like be cautious about it. But no, you're right, and it is really intriguing. And maybe we can talk about it later as well. That'd be great. Yeah.
So this is awesome. Great to see like actual new ideas. I love that. It's probably maybe for me, but so I mean, you talked about Super Mario Bros. Of course, everybody talks about Super Mario Bros. Obviously, this breaks down as soon as you introduce time because it's not equivalent. And I guess you thought as far as you could sort of you take away time and then you sort of see the equivalence in absence of time. Now, isn't this concept even more useful the more you abstract away features of the game? Because what we really want is like equivalence between big chunks of like having entered the room and not having entered the room, like all of these states that are sort of similar or equivalent. Could you fussify this?
Yeah, I'm really interested in that, and you're right. The exact thing we say in the paper is, if we're going to do Mario, we're going to remove the timer. That's probably what you would do, but of course that's expert knowledge, right? So which I'm dead set against. So I think I'm really interested in it, and I wonder if we can build AI systems that could help construct this on the basis of reversibility later. So what I'll say is, and this is not me trying to dismiss your question, the aim of this paper was like, hyperstates are a thing, and here's how I define them. And that is like, yeah, that's like a juicy thing that we'd love to work on next. And yeah, I'm super excited. Let's have a chat. That'd be cool.
Last question?
While the microphone's getting up, I just want to say I moaned about Super Mario level generation for years, and now I have Super Mario Maker 2, and I'm in. That's fine. I'm sold. Go on.
Okay. So the question I have is if there's an action a player can take in a level that's sort of like a soft reset, like press the button to start the level over, this means that from like almost any state you can reach like the beginning state of the game. Does that cause like all states to be joined into one hyperstate then? Or what should happen in the case of like one of those kind of actions?
So there's two answers to that. One is that it absolutely does. And one of the things that I was looking at this and I was thinking, wow, mazes are a single hyperstate. Like a maze is just one hyperstate because you can always go back, you can go wherever you want. Which kind of does still, this is why I think compression tells you something about the nature of the game. Now resetting is slightly different because that's like, it's like an extra game kind of feature that is designed to like ease the player. So some people might be like, all right, certainly Angelina would never come up with that, but it might be added as a use case feature. You might argue it's out of scope of the solver, but yes, like traditionally, yeah, it makes everything compressed to one hyperstate, and you're like, well, I guess that is what it is, So there's definitely like, kind of like with Julian's question, and it's like, there are definitely things that you think, and it makes you think about it, right? It makes you think, should I exclude this? Is this part of the act of solving the level or not? I can't tell. So yeah, I didn't really answer your question, did it? But we'll have a talk.